My name is Vishal Gaur. I'm a professor at Cornell University, and I'm very happy to present our collaborative research with IndiaMART for this application of analytics competition. Our project deals with the design of a personalized recommendation system for an online B2B platform. Our team includes engineers and product managers from IndiaMART and a PhD student, Xiaoyan Liu, from Cornell. Several of us are participating in this presentation, and we will conclude with a few words on business impact from the CEO of the firm. IndiaMART is the largest online B2B marketplace in India with a market share of about 60%. The firm has more than 100 million buyers and 6 million suppliers registered on its platform, transacting in 71 million products and services across 56 industries. These range from heavy machinery and construction equipment to pharmaceuticals to clothing to bulk food items. In 2020, there were 464 million RFQs transacted on the platform, which translates to more than 1.3 million RFQs per day. This slide shows a schematic of IndiaMART's platform relevant to our project. Buyer firms arrive continuously over time by posting requests for quotation or RFQs. IndiaMART calls these as buy leads. The platform identifies which RFQ is well matched to which seller and displays them on the seller's web page dynamically when he or she logs in. When a seller logs in, he or she goes through RFQs displayed on the web page one by one and decides whether to accept an RFQ or to reject it or simply to skip to the next RFQ. Buyers don't pay anything to access the platform, and sellers pay a subscription fee that entitles them to a certain number of RFQs that they can accept per week. So seller engagement is an important driver of performance for the platform. It determines buyer satisfaction, seller satisfaction, as well as the overall revenue base and profitability of the platform. So the goal of our project is to design an algorithm to identify which RFQs to show to a seller and in what sequence in order to improve acceptance rate. This is a challenging project, and we identify a number of different issues that we have to address in our algorithm. One is that our data is extremely high dimensional in terms of product categories, locations, and attributes of RFQs across different types of products. Sellers are heterogeneous in their preferences across these, and each RFQ is short-lived and lasts for only a few days. Our data has a severe class imbalance in terms of the overrepresentation of acceptances. So with these historical data, we want to design a real-time ranking method for RFQs and demonstrate what type of improvement we can achieve in practice from an implementation. This slide shows a timeline of our project. We began in June 2019 with data collection, started our modeling in August of 2019. Once this was successfully done, in November, IndiaMART began implementation and live testing of our method. In January of 2020, we began a controlled field experiment, starting initially with 21 sellers and gradually expanding to 300 sellers. From July 2020 onwards, we have rolled out our algorithm to 2,000 sellers across all channels in the platform and are now rolling it out to 5,000 sellers. Our work benefits from several streams of literature, mainly online marketplaces and recommendation systems. Our work also derives from the literature on discrete choice modeling in terms of methodology and contributes to the work on estimation of under high dimensional data and on practice-based research. So altogether, our work has two kinds of contributions, those based on a data-driven algorithm and those derived from the live implementation. From the algorithm, we create seller-specific metrics of closeness to address high dimensionality, and we design a new resampling strategy called Panel Data Augmentation to address class imbalance. From the live implementation, we gain insights about the performance of the method that we will describe, lessons for our team, as well as insights into the behavior of the machine learning algorithm during the sudden change that was caused by pandemic lockdowns. Specifically, because our method is based on history or recent history of seller transactions, it was quickly able to learn from the new atmosphere and adapt to showing PPE, ventilators, hand sanitizer, etc., those kind of buy leads or RFQs at the top. This was extremely beneficial in terms of the impact of the algorithm. Now, Xiaoyuan Liu will take you through our model.
In our setting, RFQs arrive sequentially to the platform, and their attributes include product category, geographical location, and other attributes such as order value. A seller's response to an RFQ is either an accept or a reject. And a seller's engagement history contains both accepted and rejected RFQs. We model a seller's binary choice for an RFQ by constructing an attribute-based logit model. In this model, a seller's decision is based on his latent random utility, which is a function of RFQ attributes. As part of the predictive analytics, we first estimate our model coefficients using historical data. We then predict the acceptance probability and binary choice of a seller for an RFQ. The predictions of the binary choice outcomes are also used for our offline model validation. In our online deployment, we use the predicted probabilities of new RFQs to render web pages to visiting sellers. In the predictive analytics, we encountered two challenges. The first challenge is in the estimation of the model due to high dimensionality and heterogeneity in our data. Our data shows that there are a large number of product categories and locations with seller engagement. However, most sellers have only engaged with a small number of product categories and locations. As we can see from these visualizations, among the 14,000 product categories, 71.5% of the sellers have only engaged with fewer than 100 product categories. Among the 9,000 physical locations, 61.2% of the sellers have only engaged with fewer than 200 locations. Seller heterogeneity contributes to this pattern. For instance, a seller in chemistry in northern India may have different category and location preferences than a seller in machinery in western India. The second challenge is the severe class imbalance in our data. The two classes in a seller's response are accept or reject. Our 2018 data is highly skewed. 97% of the records are accepts, and only 3% of the records are rejects. We identified 3 potential causes of class imbalance in our context. One is seller inertia to provide negative feedback. Another cause is that data on available RFQs viewed but not acted upon are not available. Feedback cycle from the existing recommendation system also contributes to class imbalance. Severe class imbalance results in poor predictive performance with respect to recall of rejects, which can give rise to the system recommending irrelevant RFQs to sellers. So to mitigate class imbalance, we devised a new resampling method and evaluate alternatives. Our original dataset contains 1,000 sellers and about 900,000 transactions. 97% of the records are accepts. From our original dataset, we first curated a sample based on 20 representative sellers, and class imbalance reduced to 64% of accepts. SMOTE is a method proposed in the computer science literature. We use SMOTE to generate synthetic rejects by random interpolation. PDATE is the new method that we propose, which stands for Panel Data Augmentation Technique. And PDATE also mitigates class imbalance by generating synthetic rejects. At a high level, PDATE method leverages data for other sellers from the same time window. For an accept record, we first identify the pool of RFQs engaged by other sellers within the same time window. And then we randomly infer a synthetic reject from this pool. One observation to highlight from our model fitting results is that the frequency and geography variables have a significant predictive power. These variables are seller-specific and time-evolving. Constructing these variables is our approach to tackle the estimation challenge imposed by high dimensionality and heterogeneity in our data, as we've seen earlier. Our results show that resampling can dramatically improve performance. Specifically, recall for rejects has improved from 29% under the original sample to 50.6% under Q-rate, 84% under SMOTE, and 69.1% under PDATE. And recall for accepts has remained as high as 90% across all the resampling methods. Now, Gaurav Manchanda, who is a senior product manager at IndiaMART and the project lead for our team, will describe the field experiment, implementation, and business impact.
We'll now talk about the rollout of the model and how we conducted field experiments on IndiaMART sellers to judge its efficacy. We rolled out the first version of the model in January 20 on a small user set of 21 sellers. We wanted to test the waters and see how well it performed compared to our existing non-ML based recommender engine. We selected a control set of 63 sellers who had similar features as our test set and were shown recommendations from non-ML engine. We did a difference in difference analysis on both sets to compare relative performances. We call this as the phase 1 of the implementation. Then on March 23rd, a nationwide lockdown was announced in India as preventive measure against the COVID-19 pandemic. We saw a decline in the transaction volume for both the test and the control set during this time, which I will show in my coming slide. We continued working on more features for the model and were able to develop and deploy title math score in April 20. The lockdown was eased out on 31st May and economic activity started reviving. We built some more features and gradually scaled to 300 sellers by the end of July. At present, the model is live on 2,000 sellers, and we plan to scale it to all paid sellers eventually. Talking about the results of our field experiment, we see that the transaction volume per seller has remained somewhat consistent in the first phase of the implementation for both the sets. We see a major dip in volume during the lockdown period. On the ease out of the lockdown, in the second phase of our experiment, we again see an improvement in the volume, more so for the ML sellers than the control set sellers. On the right, you can see that our leading performance indicator, which is contribution of transactions from top 25 ranks on the page, has been improving consistently despite the pandemic, as we kept adding more variables and kept refining the model to make it robust. This slide highlights in greater detail how transactions have improved from the top positions of the page. We have shared positional data of the ML set for 35 days before going live and compared it with the performance in 189 days after implementing the model. We see an improvement of 5 percentage points from 59% to 64.1% in transactions from top 10 positions. The transactions from top 25 positions also improved by 8.5 percentage points from 75.9% to 84.4%. We've also seen a significant improvement in the mean rank of transaction position, which has gone from 37.95 to 16.21. As mentioned, a difference in difference analysis with respect to the control set was done to conclude our results. Similar improvement in top 25 contribution and average rank were also seen in other sellers as well when we scaled from 300 to 2000 sellers. We now talk about some of the surprises we saw and the lessons we learned in this journey. We did a lot of case studies, conducted user interviews, observed videos of users interacting with the platform, particularly the RFQ page, studied their frequency of visits on the platform and other parameters to comprehend how they were behaving and their motivation of selecting an RFQ. This has helped us design more robust features in the model and also helped us understand our sellers better. We learned that the user wants to see an assortment of leads from his preferred product categories and his preferred geographical area. The users who frequently visited the page wanted more recent RFQs every time they logged in, and the less frequent ones did not focus much on the recency of RFQ, but on other parameters. Now, Rukhsar Shakir, who is a lead engineer in my team, working on this project for the last 2 years, will describe some of the technical challenges we faced during the implementation and how we tackled them.
Thank you, Gaurang. I, being at the model deployment end, want to share a few lines about my experience. I was majorly responsible for end-to-end design and setup of the data pipelines, deployment of variables, and maintenance of infrastructure. We have implemented, tested, and maintained the infrastructural components for proper data collection, storage, and accessibility, and we are finally ready with a system which processes about 10,000 RFQs, request for quotations per minute in real time, and distribute them among the 2,000 users. I have faced many challenges in researching the technology pain points, proposing technological solutions, and carrying out the implementation. We expose the model by an API which uses the variables and apply ML model to it to get a probability value, and then finally displaying the results to the end user from a cached database according to the probability. As per the coding language part is considered, we have used Python to apply ML model to the input variables and save the probability in the database. We have used RabbitMQ to get event-based data in the queues, such as mapping the latest data for the user, deleting an expired data for the user. And for the display API part, that is for displaying the results to the end user, we have used Golang as the coding language. Now our CEO, Mr. Dinesh Agarwal, will summarize the relevance of this machine learning project to IndiaMART from his perspective.
We at IndiaMART have started to get good success at machine learning at large scale problems. I remember this particular problem was one of the most difficult ones. We have been solving that by way of rule-based engine that we had, and slowly taking feedback and making manual intelligence into the rule-based engine. And this is one of the very complex problem where every customer has a different behavior, has a different geographical behavior, has different categorical behavior, as well as seasonal behavior. Some people use the platform very frequently, and some people use the platform very occasionally. To make all that fall in one single algorithm is not an easy task. And unlike the consumer personalization, here it is a B2B personalization. Supplier's time is very highly valuable, and they get dejected when even one single unrelated recommendation is thrown to them. And today I'm very happy to say that we have already deployed it on almost 10% of our customer base with equal or better outcomes than our rule-based algorithm. And in this particular year, we are going to deploy it across all the customers.
To conclude, we are now working on a number of next steps, which include building an improved model by using text data and seller behavior metrics that are customized to each seller. We are expanding the scale of our implementation, and we are working to integrate machine learning into the business by building a sandbox that allows us to create a much faster cycle of experiments and testing. Thank you very much.